Hi, and welcome back to the first video of the 12th and last lecture in this course on Covidenomics. In this first video, we're going to look at a simple question, which is, do governments use the best information to design policies? There's been some criticism of various governments around the world and their reaction to COVID-19 and the policies that they have adopted. Here in Australia, Richard Holden has written in The Conversation about the difficulties governments might face in changing their minds, that might be viewed as by the electorate as reflecting weakness, or that they made initially the wrong decisions. There's a whole literature on political science that I'm not going to get into. I'm not an expert in that area, and it goes well beyond the scope of this course. But I do want to give you a bit of a flavour for the sort of problems that face governments, given that in democracies they need votes, and votes mean that they need to convince the public that they're worth voting for. And convincing the public that they're doing the right thing and actually doing the right thing is not necessarily the same. Now, before we get into any of this, this is going to be very simplistic, so apologies for that. It's going to be the simplest possible model that I know of that's robust. Also, not in any way claiming that governments should do something different, that we should have a different voting system or anything like that. I like living in a democracy. I like the freedoms that go involved with it. And so this shouldn't be viewed as a criticism or in any way a cynical view of government in democratic countries. Rather, it's simply pointing out that governments face incentives, and we have to take government's incentives into account when thinking about what governments will do. The base model that I'm going to use here is from Adam Brandenberger and Ben Perlak, an article in the Rand Journal of Economics from 1996, when managers cover their posteriors, making decisions the market wants to see. Their particular model was designed to understand managerial incentives, but their basic model applies equally as well to governments and thinking about government incentives. To better understand the problem facing government, let's just run through a simple example. Suppose that there are two policies. We've got a policy A and a policy B. One of these policies is better than the other. The trouble is that we're not sure up front which one is better. Now, the electorate don't know for sure which is the better policy, but they do have a probability, what's often called a prior or a prior belief about the policies. And that prior belief is given by this number pi, which is greater than a half, and that's the belief in the general population or the electorate that policy A is the better policy for the government to pursue. For example, suppose that our two policies, policy A might be, say, a hard lockdown, and policy B might be a soft lockdown, say in response to a second wave of infections of COVID-19. Then our assumption here is that this probability pi is the electorate or the general population's belief about whether a hard or a soft lockdown is better. And our assumption that pi is greater than a half says that the general population, overall they think that a hard lockdown's probably better in a second wave, but they're not sure. Or another way to think about it is that if you took a random sample from the population and asked, should the government have a hard or a soft lockdown as we enter this second wave, more than 50% of the respondents would say hard lockdown, and less than 50% of the respondents would say soft lockdown. We can think of that pi as being that share of the population who prefer the hard lockdown, who think that's the better policy. The government, however, has private information. It gets information from the best possible experts. It's got data that isn't generally available to the public. It's able to have discussions with overseas leaders and see what's happened there and learn from overseas. So we take this as the government having private information. The government gets a signal. We're going to summarise all of that information just by a single signal. And the signal is either A or B, little a or little b. A signal of little a is more likely if policy big A is the better policy. And signal little b is more likely if the policy big B is the better policy. For simplicity, we'll assume that those probabilities, those conditional probabilities are the same. So the probability that the government is told little a, given that big A is the better policy, is going to be given by Q, which is greater than a half. And similarly, the probability that the government sees signal B, given that capital B is the better policy, is given by Q, which is greater than a half. We can think of this information as the government consulting experts that are at hand and also learning from overseas. So for example, policy A here, which is the hard lockdown, the government will talk to the epidemiologists and say, look, what have we learnt about this virus? Do we need another hard lockdown? It will talk with the people on the front line in the hospital emergency care facilities and ask, how many people are dying from the virus? How likely is it that people will die? How better are we able to treat them now than we did before? The government will talk to the economists and say, what was the cost of that first lockdown? What were the problems there? The government will talk to other health experts, such as mental health experts, such as people involved in the treatment of other serious and potentially fatal diseases like cancer. How did that first lockdown affect treatment? How did it lead to a spike in cases? Did it lead to stopping coronavirus deaths, but lead to other deaths, for example, through mental health issues? The government will talk to overseas leaders. How did your lockdown go? What did you do? Were the costs of your lockdown more or less than ours? How did you manage your track and trace, your alternatives? And it's bringing all of that information together, which is what we mean by this signal to government. So if a government gets this signal little a, means that overall that private information, that information that the government's got says, yep, we need a hard lockdown to deal with the second wave. If government gets small b as its private information, then it's really saying the best evidence that we've got is, yep, the hard lockdown was good straight off when we didn't know much, but we have learnt enough now so that actually a softer lockdown with other strategies, other non-pharmaceutical interventions will be a better way of dealing with this virus. Now, the interesting case is going to be where Q is greater than pi. What that means is that this private information that the government gets is accurate enough or robust enough to outweigh that prior belief of the population. So the reason why Q has to be bigger than pi is that if the government gets signal B, then the government still has that general community information, yep, probably a lockdown, a hard lockdown's better, but if it gets signal B, it's got to say, now I've got extra information, does that make me change my mind? And we need Q to be bigger than pi for the situation to be when the government gets little b as a signal, the government will want to change its mind and not do a hard lockdown, policy capital A, but a soft lockdown, capital B. So the government gets this private information, and you can easily check that under the assumptions we've made here, the government, if it wants to maximise the outcome for society, then it will follow its private signal. That just follows from Bayes' rule. We're going to have a bit more detail on Bayes' rule in the detour in the next video. If you want, you can check it for yourself. But the assumptions we've got here say that if the government observes little a, well, that just builds on the prior probability. Pi, remember, is the probability that capital A is the better policy without any extra information. So if they get more information that says, well, yeah, capital A is really good, clearly capital A or big A is the better policy. But if the government gets little b, then given our assumptions, Bayes' rule says that capital B is more likely to be the better policy compared to capital A. In other words, the best policy is not the one that the general electorate or the majority of the population think is the better policy. The government has more information and knows that in fact capital B will be the better policy. But what does the government actually want to maximise? Well, governments don't necessarily want to maximise policy outcomes for their country. What they want to maximise is votes. They want to maximise the chance of being re-elected at the next election. And that's where the problem of complication comes in. Suppose that between the time that the government chooses the policy and the electorate is able to see the outcome of that policy and determine whether it was the right policy or not, there's going to be an election. Now, that's not an unreasonable assumption, because it can take years, decades, a very long time to actually work out whether policy capital A or policy capital B was the better policy. In fact, you may never be able to work it out. So it's reasonable that a 3 or a 4 year election cycle, often the government will be making decisions about policies when its eye is really on the next election, because the electorate is only going to really work out the outcome of the policy choice after the next election. Now, voters want to support a government that's made the right policy choice. But clearly they have to vote before they know exactly what is the right policy choice. So voters will support the government if they think the government has made the right policy choice. So the voters are going to have their prior probability, pi, that capital A is the better policy. They're then going to know that the government receives private information, but the government has a whole lot of access to information that the general electorate don't have. They're going to see the government choosing a policy, and they're going to support the government if they think the government has chosen the right policy. Indeed, they're going to be more likely to vote for the government the more certain they are that the government has made the right choice. In other words, the higher the probability that the electorate has that the government has made the right choice, the higher the votes for the government. If the electorate thinks, well, there's a 51, 52% chance that the government's done a right policy choice, pretty much a flip of the coin, they'll support the government a little bit. But if they think that the government has definitely made the right choice, say a 90% chance, they'll strongly support the government. Of course, if they think the government's made the wrong policy choice, or in other words, the probability that they've made the right choice is less than 50%, then less than 50% will vote for the government, and the government will be more likely to lose. So in this situation, we're going to assume that the government wants to maximise its vote by having voters think it has made the right policy choice. Now, this may seem rather cynical. The key assumption here is that the government wants to maximise its vote, not that the government wants to do the right thing. Okay, that's an extreme assumption. Governments will often want to do the right thing and maximise their vote. But let's run with this extreme assumption to see where it leads us. Because thinking about a government wanting to maximise its vote, which is not unreasonable, can lead to some pretty serious policy outcomes. In particular, it leads to the following claim. In this situation, where the government wants to maximise the probability that the electorate thinks it has made the right policy choice, in this situation, there cannot be an outcome where the electorate believes that the government will always follow its own information and choose the best policy. And in this outcome, we know that the government will in fact not actually always follow its own information, even though, as we've already noted, given our assumptions, the best thing for society is if the government follows its own information. I want to be careful that I'm clear on what's being claimed here. I'm not saying that the government never follows its own information. What I am saying is that regardless of whether the government sees signal A or signal B, there cannot be an equilibrium where the government always follows its own information, even though we know that the best outcome for society is if the government always follows its own information. So all I'm saying here is that, in a sense, the government will be compromised by its wish to get re-elected, it will sometimes not choose the best policy. Not that it always chooses the wrong policy, just that sometimes it will choose the wrong policy. Or in other words, it cannot be the case that it always chooses the best policy. So what I'm really claiming here is a negative result, in the sense that we know what we want the government to do, the government will not always do it. The result is actually pretty clear from Bayes' rule and our definition of a Nash equilibrium. To see that, let's just use a simple example and work through it. So I'll make pi equal to 0.6. So before the government has any information, the electorate believes with 60% chance that policy capital A is the better policy. Again, we're using it here as a hard lockdown. So 60% of the electorate would favour a hard lockdown, 40% would favour a soft lockdown. We're going to assume that Q equals 0.7. In other words, when a hard lockdown is the better policy, there's a 70% chance that the government will receive signal little a, and only a 30% chance the government will receive signal little b. However, if a soft lockdown, capital B, is the best policy, then there's a 70% chance that the government will receive signal little b, and a 30% chance that the government will receive signal little a. Now, remember, what we're interested in here is whether capital A or capital B is the better policy. The government needs to take into account the prior information that's captured by our pi, our 0.6, plus its private information captured by its signal. It does that through applying Bayes' rule. To see how we apply Bayes' rule in this situation, let's just draw up this little table here, which is actually a Venn diagram, and it's just going to capture the possibilities of all our outcomes, either policy A being better or policy B being better, and whether the government sees signal little a or signal little b. They're mutually exclusive alternatives. It sees either A or B, and similarly, either policy A is better or policy B is better. They're mutually exclusive alternatives. Our prior probability, that pi, tells us that without any information, there's a 0.6 chance that A is better and a 0.4 chance that B is better. That's just our value pi. Now suppose you see signal A. So we're in this top row here. Our conditional probability tells us there's a 70% chance that if we've seen signal A, it's because A is better. So we're in this left-hand box. And there's a 30% chance that we're actually in the right-hand box. Similarly, if we see signal B, we know we're in this bottom row. There's a 70% chance we're over here, because the chance of seeing signal B, given that B is better, is 70%, and a 30% chance that we're over here in this box. So now we can work out the ex-ante probabilities of each of these boxes. And those are given by these numbers here. For example, the chance of A being better and receiving signal A is given by 0.42. There's a 0.6 chance that we're in this column. If we receive signal A, there's a 0.7 chance that we're going to be in the left row rather than the right, left column rather than the right column. So it's 0.7 times 0.6, 0.42 is the probability that both A is better and we receive the signal little a. Similarly, if we see signal A, then the chance of us being over here is 0.3. The ex-ante probability that B is better is 0.4, so our ex-ante probability of B being better and seeing signal A is 0.4 by 0.3, 0.12. Similarly here, 0.3 by 0.6, and 0.7 by 0.4. Remember, what we're interested here is the probabilities that the government should have given the government has seen a signal. So we're interested in knowing what is the actual probability that A is better given that the government has seen signal little a, or the probability that B is better given that the government has seen signal little b. How do we do that? Well, suppose the government sees signal A. It now knows it's in this row here with probability 1. So in a sense it has to weigh up these probabilities so they add up to 1. We know that of that we've got a 0.42 probability of being here versus a 0.12 probability of being here. So Bayes' rule essentially says the probability that A is better, given you've seen signal A, given you're in this upper row, is going to be 0.42 divided by 0.42 plus 0.12. The division by 0.42 plus 0.12 is just weighting up these probabilities so they add up to 1, because we know we have seen signal A, so we know we're definitely in this row. Similarly, if the government sees signal B, the probability that B is better, well, we now know for sure we're down here in this row, so we're going to have to divide our probabilities by 0.18 plus 0.28 because they have to add up to 1, so we've got to scale everything up. And the probability that we're in this right-hand box rather than the left-hand box is 0.28 divided by 0.28 plus 0.18. And that's exactly what we've done here. So the probability that policy A is better, given the government sees signal little a, is 0.42 over 0.42 plus 0.12 or 0.77, which, as you would expect, is greater than 0.6. So the government's private information backs up the prior information. The probability that capital B is better, given the government sees little b, is given by 0.28 divided by 0.28 plus 0.18, which is 0.61. So as we said at the beginning, because of the way we've set up the assumptions here, the government should always be following its private information. The probability that capital A is a good policy given little signal A is well and truly greater than 50%, and the same probability that B is better given little b is greater than 50%. But the claim is the government cannot always do that. Why not? The way to check a Nash equilibrium is always to say, take the strategies that form a Nash equilibrium and then see if any party wants to deviate. So what are the strategies we've got here? Well, we want to test that you cannot have an equilibrium where the government always follows its private information. So we're testing the strategies that the government always chooses policy A when it sees signal A and policy B when it chooses signal B. Remember, the government's aim is to maximise the chance of it being re-elected, which means it wants to maximise its votes, which means that it wants to maximise the probability that the public thinks it's done the right thing. So the public strategies are very simple. They will vote for the party, for the government, based on the percentage that they have that the government has followed the right policy. So, in other words, if the government follows that policy, always follow your own signal, and the public knows this, they say, yep, we've got a good government here, then if they see policy A, they're going to say, well, we know there's a 77% chance that that's the right policy. We're going to vote 77% in favour of the government. If we see policy B, there's a 61% chance that's the right policy. We're going to vote 61% in favour of the government. But remember, the government's objective is to maximise that probability, the share of the vote that it gets. Suppose then that the public believes the government will always follow its information and the government sees signal B. Sees signal little b. Says, if we do policy B, we're going to get 61% of the vote. If we do policy A, the government is going to get 77% of the vote because people will believe we've seen signal A. We haven't. We've seen signal little b, but would be better off. We'll maximise our vote if we pretend we've seen policy little a. So the government will prefer to deviate. That means that we can't have a Nash equilibrium, and that is the proof of our claim. There cannot be an outcome in this situation where the government always follows its own information and chooses the best policy for the country, because because doing so will not maximise the government's expected vote. Remember, I'm not saying the government will never follow its own information. I'm not saying the government will never do the right thing. Indeed, it's pretty obvious that if it sees signal little a, it's going to choose capital A in this situation. What I'm saying is that the government cannot always do the right thing. That is not an equilibrium outcome, because the government can make itself better off by changing tack when it sees signal little b. That means that the public, quite rightly, should have some cynicism about what the government's doing, because in reality the government may be doing the right thing, but it may not. This is a very simple model that I've presented here, but in some ways it's very powerful in that it shows the limitations of democratic government. Now, that doesn't mean, by the way, that democratic government's bad. I'd prefer to live in a democracy than the alternatives, quite frankly. Nor does it mean that we shouldn't trust our governments. Because, whilst I'm assuming the government wants to maximise its vote, it may be the case that you have genuine leaders who say, no, I want to do the right thing by the country and choose the right policy based on the best information available. And of course, if a leader can get that reputation, that is a valuable reputation to have. It does mean, however, that governments will sometimes have their hands tied. That we shouldn't naively say, yep, the government's chosen this, it's the right thing to do. In the next video, I'm just going to give you a bit more detail on Bayes' rule, just a bit of background. Then what I'd like to do in the third video in this lecture is just run through some of the learnings that we've got from this course, some of the things we can take away and say, well, how do we prepare for the next emergency, whether it's a pandemic, a bushfire, a cyclone, or whatever. Talk to you then.